This lab builds an eBGP chain across Cisco routers in GNS3, then uses Ansible to push the full configuration through Jinja 2 templates and verify the results. The point is not just getting BGP up, it's proving you can deploy and validate a multi-AS topology without touching the CLI on any router. This is a linear eBGP topology. 4 routers, each in its own AS, connected in sequence. R1 peers with R2, R2 peers with R1 and R3, R3 peers with R2 and R4. Every transit link is a /29. Each router also has a loopback used as its BGP router ID and a LAN segment it advertises into BGP. The management network on 192.168.0.0/24 is separate from the data plane. That's how Ansible reaches the routers. R1 is AS65001. Its loopback is 1111. Its transit-facing interface is Fast Ethernet 00 at 10.0.1.1, and it peers with R2 at 10.0.1.2 on the same /29. R2 is AS65002, loopback 2222. R2 faces R3 on Fast Ethernet 10 at 10.0.2.2 across the 10.0.2.0/29 link. R3 is AS65003, a loopback 3333. R3 faces R4 on Fast Ethernet 11 at 10.0.33. R4 is AS65004, loopback 4444, connecting back to R3 at 10.0.34. Every router also has a LAN interface on Fast Ethernet 3.1, advertising a 192.168x0/24 prefix into BGP. Every router is its own AS, so every adjacency is eBGP. That keeps the config pattern identical across the topology. The linear chain matters because R1 has no direct link to R4. For R1 to reach R4's LAN prefix, that route has to propagate through R2 and R3 with each AS prepended to the path. If end-to-end reachability works, BGP is doing its job across 3 AS hops. The loopback addresses double as router IDs and as /32 prefixes in the BGP table, so you get extra verification targets for free. The /29 transit links are the smallest practical subnet for point-to-point on a fast Ethernet that would include all the IPs up to .4. In this lab, I am matching the IPs to the routers. .1 for R1, .2 for R2, .3 for R3, and .4 for R4. Well, this project follows a standard Ansible layout. The inventory puts all 4 routers in a single group. Group vars set the connection plugin and credentials. Each router gets its own host vars defining the host name, ASN, router ID, interfaces, BGP neighbors, and network statements. 2 Jinja 2 templates handle config generation. 1 for interfaces, 1 for BGP. Deploy.yml pushes both templates. Verify.yml collects the results. The configs directory is a snapshot of the running configs after deployment. It is not an input to anything. The BGP template iterates over the neighbor list from host vars. For each neighbor, it renders the remote AS, description, and an activate statement inside the IPv4 address family. Network statements come from a separate list in host vars. The template is the same for every router. The data in host vars is what makes R1 different from R3. That separation is the whole point of using Ansible. You write the template once. The per router logic lives in YAML, not in Jinja 2. Look at the rendered output on the right. For R3, which has 2 neighbors, the template produces 2 neighbor statements and 2 activate lines. R1 with only 1 neighbor gets 1 of each. Same template, different data. This is R1's BGP table. Every learned route has a next hop of 10.0.1.2, which is router 2. That's the only neighbor R1 has, so everything flows through this router. The 2 local prefixes, 1111/32 and 192.168.10/24, show a next hop of 0000 and no AS path, locally originated. R2's prefixes show a single AS in the path, 65002, 1 hop to this router. R3's show 65002 and 65003, 2 hops. R4, 65002, 65003, and 65004, a total of 3 hops. Each AS boundary prepends its own number, so that the path length tells you exactly how far away a prefix is. In a linear topology, there is only one path to each destination. There's nothing for BGP to select between. But the AS path attribute is still doing its job. It's recording the full forwarding chain from origin to receiver, and you can read it left to right to trace the exact sequence of autonomous systems that the route traversed to get here. Before I run the deploy, here's what the routers look like right now. On R1, I've opened up a console and I'm going to run show IP interface brief. The only interface with an address assigned is the management interface, that is fast Ethernet 3.0, with an IP address of 192.168.0.1. This IP address was assigned manually during bootstrap, and it is necessary for Ansible to work. Over on the Ansible control node, I'm going to run Ansible playbook deploy.yml. Now, the first task is configure hostname and interfaces. It runs against all 4 routers in parallel. You should see each host come back with a status of changed, meaning the template pushed config that wasn't already there. The second task, push BGP configuration. Same thing. Once again, we see that the configuration has changed across all 4 routers. Down in the play recap, look for OK and changed counts on each host. You want to see that changed is greater than 0 and on all 4 routers, and that failed is equal to 0. If you get a failure here, the most common cause is an SSH key exchange mismatched. The C7200 images I am using only support CBC ciphers and legacy key exchange algorithms. There is a note in the README showing the appropriate SSH config workaround for that. Back on R1's console, we're going to issue show IP interface brief again. And we see that all the appropriate IP addresses have been assigned to the appropriate interfaces, and all interfaces are in the up and up state. The template pushed addressing, descriptions, and no shutdown on every interface. All 4 routers got the same treatment simultaneously. Next, I'm running Ansible-playbook verify.yml. This playbook collects BGP summary and BGP table output from all 4 routers, runs assert tasks against the neighbor state, and then pings between the 2 endpoints. The first two tasks collect and display show IP BGP summary. Look at R2's output. Two neighbors, 10.0.1.1 and 10.0.2.3. The column you care about is the state/prefixed/receive column. If that shows a number, the neighbor is established, and that number is how many prefixes it has received. If it shows idle or active, the session is not up yet. The next two tasks collect and display show IP BGP, the full BGP table. On R1, you can see its own prefixes with a next hop of 0.0.0.0. This means it is a locally originated path. R2's prefixes show a next hop of 10.0.1.2 and an AS path of 65002. R3's prefixes have a path of 65002, 65003. R4's prefixes show 65002, 65003, and 65004. 3 AS hops. The path is building correctly across the router chain. On R4, the same table, but reversed. R4 sees R1's prefixes with an AS path of 65003, 65002, 65001. Path length is symmetric in both directions because the topology is linear. There is no alternate path for anything to take. After the BGP table output, the assert tasks run. Verify no neighbors in idle state and verify no neighbors in active state. You should see OK on all four routers with messages like no idle neighbors on R1 and no stuck neighbors on R1. If any session was down, the assert would fail and the play would stop right there. The last task is the reachability check. This only runs on R1 and R4. R2 and R3 get skipped, which is to be expected. R1 pings 192.168.4.254, sourced from 1.1.1.1, and R4 pings 192.168.1.254, sourced from 4.4.4.4. You'll see R2 and R3 print variable is not defined for the ping results, which looks ugly, but it's just because the ping task was skipped on these hosts, not an error. Look at R1's output. 5 sent, 5 received. 100% success. Same with R4. The traffic is crossing 3 eBGP hops in each direction. The play recap at the bottom shows OK equals 8 on R1 and R4, OK equals 7 on R2, and R3 with 1 skipped each, and failed equals 0 across the board. So before I close this out, I thought we'd do a little bit of live verification. On PC1, let's try to ping PC4. Let's ping 192.168.4.1, and we have a good ping between PC1 and PC4. Let's try to ping the loopback on R4, and we have a good ping between PC1 and the loopback on R4. Let's try the same thing on R1. Ping 192.168.4.1, that's PC4. And something curious is happening here. The ping between R1 and PC4 is not good. Let's check to see if the ping between R1 and the loopback on R4 is good. and it's not looking good here. The ping between R1 and the loopback on R4 is not good. And the question is, why is that? And the answer lies in the routing table on R4. If we take a look at that, we see that we have routes to all the LAN networks off of the routers, as well as routes to all of the loopbacks on the routers. But we do not have routes to the transit interfaces on any of the routers. So if we go back to R1 and we attempt to ping PC4 with a source IP address of 1111, we see we have success. And if we attempt to ping the loopback on R4 with a source address of 1111, you see we have success. And that is because we do not have routes between the transit interfaces and the rest of the network. So when you attempt to ping the loopback interface on R4 from R1 without specifying a source interface of the loopback address, it does not have a route back to that interface. If we attempt to ping R4, the loopback on R4, with a source IP address of the loopback on R1, we have a good ping because it does have a route back to that interface. That's a 4-router eBGP deployment driven entirely by Ansible. The only CLI work required on each router is the bootstrap. This consists of assigning a management IP, creating a username and password, and generating the crypto keys for SSH. Once that is done, Ansible owns everything else. The templates and host vars handle the logic separation, the deploy playbook pushes it, and the verify playbook proves it worked. If you want to add a 5th router, you'd write one more host vars file and rerun the playbook. The topology scales without the workflow changing. All the configs, playbooks, and templates are in the GitHub repo linked in the description.